Hello dear students. I welcome you all on behalf of Shri Jayendra Rank Zone classes. In the previous lectures of wave optics, we have learned about the resolving power, the diffraction patterns, experiment for diffraction, etc. Now let us solve some previous year comparative exams questions. This question was asked in JEE Mains 2015. Assuming human pupil to have a radius of 0.25 centimeter and a comfortable viewing distance of 25 centimeter, what is the minimum separation between two objects that human eye can resolve at 500 nanometer wavelength? The resolution power for human eye is given by theta is equals to 1.22 lambda divided by capital D. The minimum distance is x into theta. So put all the values and resolve. We will get D minimum as 30 micrometer approximately. So second option is correct. Next question. In a Young's double slit experiment with light of wavelength lambda, the separation of slits is small d and distance of screen is capital D such that capital D is very greater than small d is very greater than lambda. That means the meaning of this, there is no diffraction observed. The fringe width is beta. The distance from the point of maximum intensity of the point where intensity falls to half of the maximum intensity on either side is. The point where the intensity falls to half of maximum intensity is beta by 4. This is the next question. Two beams A and B of plane polarized light with mutually perpendicular planes of polarization are seen through a Polaroid. From the position when the beam A has maximum intensity and beam B has zero intensity, a rotation of Polaroid through 30-degree makes the two beams appear equally bright. If the initial intensities of the two beams are IA and IB respectively, then what is the ratio of IA and IB? Initially, they were mutually perpendicular. Now one has been rotated by 30 degree. So A makes angle 30 degree and B will make angle 60 degree with the axis. They both are equally bright, so the intensities are equal. So we can write IA cos square 30 degree is equals to IB cos square 60 degree. So IA upon IB is cos square 60 divided by cos square 30. That is 1 by 2 whole square divided by root 3 by 2 whole square. This will give us the answer 1:3. Next question. A diver looking outside the water sees outside world contained in a circular horizon. The refractive index of water is 4/3 and the diver's eyes are 15 centimeter below the surface of water. Then what is the radius of circle? Here, if outer world is seen as circular horizon, this is the radius, the depth is 15 centimeter, and the light is incident at critical angle C. So we can write 10C is equal to depth D divided by R. So R is D upon 10C. D is 15 centimeter. Divided by 10C can be written as sin C upon cos C. For critical angle, we can write sin C is equals to 1 upon mu. That is 3 by 4. So cos C will be equal to under root 1 minus 9 by 16, and 10C will be equal to 3 by root 7. So R will be 15 divided by R will be equal to, if this angle will be theta C, so R will be equal to D10C. That will give us the answer 45 divided by root 7. So fourth option is correct. The next question. Using monochromatic light, beams of intensity 16 and 9 units are interfering. The ratio of intensities of bright and dark parts of the spectrum pattern is. Here it is given that I1 by I2 is 16 by 9. So A1 square by A2 square is 16 by 9. A1 by A2 is 4 by 3. I maximum by I minimum is given by A1 plus A2 divided by A1 minus A2 whole square. So this will give us the answer 49 by 1. So fourth option is correct. Next, interference pattern is observed at P due to superimposition of two rays coming out from source S, as shown in figure. From source S, two light rays are reaching to point P, one directly and one by reflecting from the surface R. The values of I for which, the values of L for which maxima is obtained at P is. Here, two rays are reaching to point P and they will have some path difference. The path difference should be multiple of 2n minus 1 lambda by 2. Here, the path difference between the two lights approaching at point P is SRP minus SP. That is equal to 12 upon sine 60 degree minus 12, and that should be equal to 2n minus 1 lambda by 2. Solve this and we will get L is equals to 2n minus 1 root 3 lambda divided by 4 into 2 minus root 3. So third option is correct. In an experiment of single slit diffraction pattern, first minimum for red light coincides with first maximum of some other wavelength. If wavelength of red light is 6600 angstrom, then what is the wavelength of first maximum? Here n lambda for red is equals to 2n plus 1 lambda by 2. So We can find lambda as 2 into 1 into 6600 divided by 3. So lambda will be equal to 4400 angstrom. Second option is correct. A ray of light is incident from a denser to rarer medium. The critical angle for the total internal reflection is theta IC, and Brewster's angle of incidence is theta IB, such that sine theta IC upon sine theta IB is mu, that is equal to 1.28. What is the relative refractive index of two media? Here it is given that sine theta IC upon sine theta IB is I. Sine theta IB is equal to we can write tan theta IB is equal to 1 upon mu is equal to mu. So sine theta IB upon cos theta IB is equals to mu. So 1 upon mu square is equals to 1.28. So mu will be equal to 0.8. So third option is correct. Next question. In a Young's double slit experiment, the distance between the two identical slits is 6.1 times larger than the slit width. So D is 6.121 times larger the slit width. Then the number of intensity maxima observed within the central maximum of single slit diffraction pattern is. Here, the number of maxima present will be 12. Next, a ray of light of intensity I is incident on a parallel glass slab at point A as shown in the diagram. It undergoes partial reflection and refraction. At each reflection, 25% of incident energy is reflected. The rays AB and A', B' undergo interference. Then what is the ratio of I max and I minimum? I max by I minimum is given by A1 plus A2 divided by A1 minus A2 whole square. If we have incident light of intensity 100, then with first reflection 25% is reflected and 75% is incident. Again at this point 75 by 4% is reflected by this incidence. So finally, after refraction, 3/4 of 75 is refracted in the medium, that is A2. So put this values in this equation of I max by I minimum and solve it. We will get the ratio 4:1. And identical waves, each of intensity I naught, interfere with each other. The ratio of maximum intensities, if their interference is coherent and incoherent, is here. For coherent interference, intensity is n square I naught, and for incoherent, intensity I dash is n I naught. If we take the ratio, we will get the answer n. So fourth option is correct. A thin glass plate of thickness 2500 by 3 lambda, where lambda is the wavelength of light used and refractive index mu is 1.5, is inserted between one of the slits and screen in Young's double slit experiment. At a point on the screen equidistant from the slit, the ratio of intensities before and after the introduction of glass plate is. Here, before the introduction of glass plate, the intensity is, let's say, I1, that is equal to 4 I naught. Now, after the introduction of glass plate, let's say intensity is I2, that is equal to 4 I naught cos square phi by 2. The path difference due to glass slit will be delta x, that is equal to mu minus 1 into t. So delta x will be 2500 lambda divided by 3. The phase difference is given by 2 pi by lambda into delta x. So the phase difference will be equal to 2500 pi divided by 3. So I2 will be 4 I naught cos square phi, that is 2500 pi divided by 2 into 3. So I2 will be equal to 4 I naught into 1 by 4. Taking the ratio, we will get I2 by I1 is equals to 1 by 4. So I1 by I2 will be equal to 4. So option 3 is correct option over here. Just the next question. Two coherent point sources S1 and S2 are separated by small distance d as shown. The fringes obtained on the screen will be. Here on a circle, path difference will be same locus of points having same path difference will be circle. So fringes will make concentric circles. The source is at some distance from obstacle. Distance between obstacle and the point of observation is b, and wavelength of light is lambda. The distance of nth Fresnel zone from the point of observation is. Here we can use the direct formula b plus n lambda by 2. This is all for today, and with this our chapter ends here. Thank you and all the best.